This is a student, Shirley. As living outside the campus, she has to drive to her university every single day. When she turns into the campus, the road ahead is completely jam-packed with cars. "I'm going to be late," Shirley shouts. All around, drivers are anxious. What's causing the jam? Actually, it's a stop sign at a pedestrian crossing. At many crossings on campus, stop signs manage traffic. Vehicles must come to a complete stop and wait for all pedestrians to cross. But during peak hours, like when classes change, the flow of pedestrians and cars becomes overwhelming. Drivers are stuck waiting for several minutes, and the traffic is so slow. As a result, the university has to hire traffic officers during these times to help manage the crowds. But it doesn't help much. To solve this problem, the university installed an intelligent traffic light at a busy crossing. This system has a lot of cameras and sensors, uses computer vision, machine learning, and cloud computing to analyze traffic flow. It dynamically switches the right-of-way between pedestrians and vehicles, keeping everything moving. After the system was installed, the traffic jam disappeared. The university no longer needed traffic officers, and everyone got to their destination faster and stress-free.
Now, we see a problem has arisen. We have realized that the past solutions were not efficient. But why? What did we do? Why did it fail? In the past, we relied on stop signs and manual control. Let's check what happened. During rush hour, many people need to cross the road. They keep coming in a steady stream. But often, the stop's instructions don't work. These two methods both have disadvantages. For stop signs, there's a long waiting time, and there's no response to emergencies, and people may not follow the rules. And for manual control, it means high labor costs, and the capacity of staff is not unlimited. Also, there's a non-compliance risks. That's why the problem still exists. What about traditional traffic lights? Well, it brings a bigger problem. As you can see, during non-peak hours, people have to wait unnecessarily, wasting time, and it's inefficient. To put it simply, it's good, but not good enough. It cannot adjust to changing traffic conditions. They create unnecessary waiting during quiet times. Again, they don't account for emergencies. Beyond ambulances, even private drivers might have urgent needs. And that's why these methods failed. So, what are we looking forward to? We hope for a smarter, intelligent traffic light. When there are many people, it gives pedestrian a green light. When there are fewer people, it lets vehicle pass. We hope it can smartly detect such situations. So, how to implement this kind of smart? First off, we can start with a regular traffic light. To check traffic, we'll add some eyes, like cameras and microphones. And we get a cloud platform. The camera takes picture and send to cloud. The microphone records audio and send to cloud. The cloud processes it and gives the traffic info back, and light changes. That's an intuitive and feasible idea. We can call it a smart traffic light. It's a real-time detection. It uses camera to count pedestrians and vehicles dynamically. It uses microphone to identify emergency zones to give green lights when needed. By processing data, it changes light timing based on the traffic flow. And so, we can get a safer and more efficient intersection. That's a smart traffic lights. Smart traffic lights sound great, but the market already has many mature products, often part of complex intelligent traffic systems, named ITS. For example, EconoLight and CMU Surtrack, Digi International, Siemens. These companies have launched advanced systems. So the question is, why choose us? Let's take a look at the challenges with current ITS systems. First, Most ITS solutions are built for large-scale urban traffic management. They are complex and integrated solutions. Second, they are very expensive. The hardware and maintenance costs are extremely high, like infrastructures, some numerous sensors. Third, there are privacy concerns. Data like driver location, Wi-Fi device info, or even facial data raises privacy and security issues. And finally is the compatibility issues. They are not compatible with older systems, and upgrading may lead to a costly replacement. In short, they are too complex and too expensive for campuses. They are unwilling to tackle these so-called small pain points. What about us? Well, we focused on enclosed environment, saying campuses, factory parks, or similar spaces. Our product is tailored for small, closed environments. We solve the intersection-specific issues like pedestrian vehicle crossing. We only need to focus on several key points. And it's just a simple combination of cameras and microphones. No need for overcomplicated or city-scale solutions. And it's lightweight and easy to deploy. In short, our solution is targeted, scalable, and affordable. Let's check the cost comparison. As you see, it costs only $200 per intersection. Even if you deploy it across multiple intersections, the cost is still manageable. On the other hand, existing market solutions are far more expensive, often costing millions of dollars. They are so expensive and complex that the needs of small enclosed areas like campuses are undervalued. And this is the real pain point we aim to solve.
Now let's talk about our solution and technical means. So firstly, let me show you what is our device. Our device consists of 4 Android cell phones, 1 Raspberry Pi, and 4 traffic lights covering 4 directions. It is powered by a lithium battery. Additionally, a series of backend control programs and a computer vision engine are deployed in the cloud. Once configured, our device can be placed at any suitable intersection in campus to dynamically organize traffic. Okay, let's get started with the infrastructure of our device. So the first question is, how is the device powered? Our device is equipped with a high-capacity lithium battery that powers the entire system. The battery provides 2 voltage buses, 12 voltage and 5 voltage. The 12 voltage system powers the traffic lights, while the 5 voltage system powers the Android cell phones and the Raspberry Pi. This design ensures the device can operate portably at any intersection without relying on any kind of external power supply, which is so good. And the following question is, how does the device connect to the network? And here, networking involves 2 components: a local network for internal sensor communication and an internet connection to the cloud. The Raspberry Pi serves as the core of the device networking. It handles communication between all sensors, all traffic lights, and the cloud. Therefore, the Raspberry Pi has to connect to the internet via campus Wi-Fi, and at the same time, it also has to play a role like a wireless access point to provide network support for the 4 Android phones and other sensors. Well, an interesting question is, how do the cameras recognize traffic? As we know, traffic processing involves 3 main steps: image capture, cloud analysis, and signal updates. Once the device is activated, the backend control programs in the cloud communicate with the Raspberry Pi to direct the phones to capture images of all 4 directions at dynamic intervals. These images are uploaded to the cloud, where the computer vision engine powered by YOLO quickly analyzes the image to detect the state of vehicles and pedestrians. The analyzed traffic data for each direction is then sent to the signal update model, which uses machine learning to update the traffic lights in an orderly manner. Also, in order to save power, we have the sleep mode. How is sleep mode implemented and why is it necessary? As a battery-powered device, energy efficiency is pretty crucial. To be honest, the device does not need to operate 24/7 in most scenarios, but only during peak traffic hours. To address this problem, we designed a two-level sleep mechanism: light sleep and deep sleep. For a light sleep mode, when traffic is minimal, it's just like the amount of the vehicle and pedestrians is below a defined threshold, which means that a traditional stop sign is enough. Then our device will enter the light sleep mode. In this mode, cameras take photos only once per minute, and the traffic lights switch to a flashing red for vehicles. Power consumption dropped to just 20% of active mode. It's pretty good, and the device can quickly wake up when traffic increases. For a deep sleep mode, during late night hours, the device enters deep sleep. Only the Raspberry Pi and one cell phone remains in the low power state, while other phones and traffic lights shut down. Importantly, the Raspberry Pi includes a YAM-Night-based audio trigger, which listens for emergency vehicle sirens or gunshots. If such sounds are detected, the device will wake up immediately and alert the administrator. Now, I guess you may worry about a huge issue of network stability. So what happens if the network or server downs? Although our device relies heavily on cloud-based computer vision, it can still maintain basic traffic light functionality during network outages. This is achieved through a software watchdog mechanism. If the network, server, or even the main programs running in Raspberry Pi fails, the watchdog takes over immediately. It manages traffic by flashing red lights for vehicles and showing walk signals for pedestrians, just like a stop sign. This ensures the device maintains minimum functionality, preventing traffic congestion or safety hazards in the worst-case scenario.
We use Google Cloud as our cloud platform. We deploy the YOLO model to process the images and get the traffic flow information. We deploy the YAM-Night model to process the audio file and classify the type of the sound. We use Flask to deploy these two services. And data will be asynchronously sent to the scenes board to visualize. Here's another question. Did we make it better? We use simulation as a proof.
This is a normal traffic situation, but when there are many cars gathered, another lane is clearly empty. Yet due to the traffic lights, we still have to wait for a long time. Therefore, with our designed intelligent traffic light system, which greatly improves the efficiency of vehicles' passage. Then we write a simulation program to test our efficiency. With configurations of fixed 20 green, 5 yellow, and 6 red cycles with separate pedestrian phase. We get our final test result, which is our average waiting time. We can now see our intelligent system offers us lower average waiting time.
Here is some of our reference material. And this is a simple conceptual diagram we designed. Well, in summary, this is our project, CampusFlow, an intelligent traffic light control system for campus roadways. We strive to harness existing knowledge and technology to tackle real-world pain points. We hope it can offer some help and inspiration. A big thank you to our team for their dedication and to you for your time and attention.